So now that we've sort of laid the groundwork with these probability distributions and some concepts from probability theory, we're going to move now into statistical inference, which is really the powerhouse where we use all that probability information to really help us do business analytics. So the learning objectives in this chapter start with describing the sampling distribution of the sample mean. And then we're going to talk about describing the sampling distribution of the sample proportion. So these go sort of, hand in hand. And then we talk about constructing a confidence interval for the population mean and a confidence interval for the population proportion. And then we're going to talk about conducting hypothesis tests for the population mean and a hypothesis test for the population proportion. So I think some of this stuff you may have covered already in Business 210. We're just going to get into it a little bit more. And we're heading towards actually performing these types of analyses on data. Okay. So let's start out with an introductory case, and it's some data that was collected on undergraduate study habits. So apparently today's college students, the question is, are they studying hard or hardly studying? So a study asserts that over the past 6 decades, the number of hours that the average college student studies each week has been steadily dropping. Back in 1961, students invested around 24 hours per week in their academic pursuits. And Susan Knight, who's a dean at a large university in California, is wondering if this study trend is reflective of the students at her university. So this is a study that was done nationwide, right? So she wants to know, do my students line up with this? Are they different? Are they the same? So she randomly selects 35 students, and she asks their average study time per week in hours. So this is a list of 35 numbers representing the study time in weeks. And she wants to use this sample information for the below task to determine if the mean study time of students at her university is below the 61 national average of 24 hours per week. And then she wants to determine if the mean study time of students at her university differs from today's national average of 14 hours per week. So in order to answer these questions, we're going to get to where we can answer these questions by what we learn in chapter 5. Okay, sampling distributions. So in many applications, we're interested in the characteristics of a population. It's difficult, if not impossible, to analyze the entire population very frequently in populations that matter to us. So what we want to do is we're going to make inferences about those characteristics based on some random sample. There's only one population, but many possible samples. So a population parameter is a constant, although its value may be unknown. Okay. It describes a characteristic of the population. The population mean describes a quantitative variable, and the population proportion can describe a qualitative variable. A statistic is a variable whose value depends on a sample. Okay, so up here with parameter, we're talking about the whole population. Then we take some sample, and then we can get a statistic off of that sample. And it describes a characteristic of a sample, and it's one of many possible samples. Now, that statistic can be a sample mean, or it could be a sample proportion, and there's others, which we'll see too. Then we have this concept, this word called an estimator. So an estimator is a statistic that's used to estimate a population parameter. So the idea is you get a bunch of data. What do you do to it? What calculations do you do to it so that you're able to get something about this? Hold on, let me get different. What you're going after is some population parameter. and you want to know how to take all this data and come up with an estimate for it. So an estimator helps you get this population parameter from some calculation from your sample, which we call a statistic. And the estimate itself that you get is a particular value of the estimator. So this is just a little bit of vocabulary here to make sure we're on the same boat. Okay. The sample mean has this notation X with a bar on top, okay, is a variable or statistic that depends on a particular sample. It is an unbiased estimator of the population mean, mu. So we'll talk about what that means in a second. The sample mean is itself a random variable. And the reason is there's an infinite number of samples you could draw. Well, maybe not an infinite number, but there is a very large number of samples you could draw. And so it's a random variable and it has its own sampling distribution. So you can think of kind of two different things. There's the underlying population and its distribution, but now you're talking about a random sample, and in that random sample you get the mean. And then that mean of the random sample has a distribution. And it's the probability distribution derived from all means that come from all possible samples of a given size. Consider a sample mean derived from n observations. Another sample mean can be derived from a different sample of n observations. If you were to repeat this process an infinite number of times, the frequency distribution of the sample means is the sampling distribution. Okay? And it's a distribution of the sample mean, not of the underlying parameter. So let's consider a population where X represents a certain characteristic of the population. So in this population, we have the mean of X, which we call mu, and we have the variance of X, which we call sigma squared. If we take a random sample of size n from the population, and then we calculate the mean of that random sample, right? We call that X bar. The expected value of X bar turns out that the expected value of the X bar is the same as the expected value of any individual observation in X, which is the mean of the population. So note, the actual value of the sample mean may not be mu, but the expected value is. All right. Furthermore, if we do this an infinite number of times and the average of all the X bars is the same, will turn out to be the same as the population mean, mu. If that's the case, then X bar is an unbiased estimator of the population mean, mu. So we say that it's unbiased if the expected value of an estimator equals the population parameter. Now consider the variance of X bar. So the variance of X bar is sigma squared divided by n. Notice that the variance of X bar is less than the variance of X because the variance of X was just sigma, but the variance of the mean is divided by n. So the larger the sample size, the smaller the variance. Each sample will contain both high and low values that cancel one another. So that's an explanation of kind of like an intuition as to why the variance would go down, because you're talking about the variance of the mean, and the mean is averaging out extremes. And the standard error is a word that sometimes students get confused by. The standard error is a standard deviation of the sample mean. Whoops, let me do that better. So the standard error is a standard deviation, but it's a particular specific standard deviation. It's a standard deviation of the sample mean, and it's given by sigma divided by the square root of n. Okay, so let's look at an example. The chefs at a local pizza chain in Cambria, California, strive to maintain the suggested size of their 16-inch pizzas. Despite their best efforts, they are unable to make every pizza exactly 16 inches in diameter. The manager has determined that the size of the pizzas is normally distributed with a mean of 16. So at least on average, they're hitting it, but with a standard deviation of 0.8 inches. So what are the expected value and standard error of the sample mean derived from a random sample of 2 pizzas? And what are the expected value and standard error of the sample mean derived from a random sample of 4 pizzas? Well, in this case, we know that the population mean is 16 and the standard deviation is sigma equals 0.8. And once again, we are not yet at a place where we are going to determine these values. So right now they're being given to us, the population mean and population standard deviation. With this, the sample size of n equals 2 tells us that the expected value of the sample mean is 16, and the standard error of the sample mean is the standard deviation, 0.8, divided by the square root of 2, because the square root of 2 is coming from the sample size of n equals 2, goes into that square root. And that's the part that's going to change this depending on the size of your sample. So with the sample size of n equals 4, the expected value of the sample mean stays the same, but the standard error is 0.8 divided by the square root of 4 now, because the sample size went up to 4, and you can see that the overall standard error went down from 0.57 to 0.4. Okay, I just said that. All right.
Hey, can you go back to the last slide real quick?
Yeah. This slide?
Yes. Thank you.
You're welcome.
Thank you.
Okay. All right, so let X be normally distributed. It has an expected value of mu and a standard deviation of sigma. Okay? For any sample size n, X bar, the sample mean, no matter how big or small, it's also normally distributed, and it has an expected value of mu and a standard error of sigma divided by the square root of n. So for example, the size of pizzas is normally distributed with a mean of 16 inches and a standard deviation of 0.8 inches. What is the probability that a randomly selected pizza is less than 5.5 inches? And what is the probability that the average of 2 randomly selected pizzas is less than 5.5 inches? What about 4 randomly selected pizzas? So as soon as we start talking about what is the probability, right? So this is the key to understanding these questions and not getting lost in them. What is the probability? We're referring to the underlying distribution that drives the sample mean. So here we're talking about the sample mean, and we find out that it is normally distributed. So we know the population mean is 16 and the standard deviation sigma is 0.8. And if we want to answer the question about a sample of 1, we would say, what is the probability that X is less than 5.5 inches? Well, that's a sample of 1, so we just go ahead and say, well, what's using the p-norm function from R, what's the probability from a normal distribution that you get 15.5 or less with a mean of 16 and 0.8? You plug that in, and out comes 0.266, or approximately 26.6% probability. With a sample size of n equals 2, we have to modify the standard deviation. So here's the key. Now we have this normal distribution. We know it's normally distributed, but the key is that we have to adjust the standard deviation that is going to go into the function. And it comes out to, it's 0.8 divided by the square root of 2. And if you did that in R, you'll have a bunch of decimals. So if you really want to be precise, you just go ahead and put that in as 0.8 divided by the square root of 2, directly typed in like that into your function in R, as opposed to introducing round-off error by putting 0.57. And if you put that in, you see that the probability of the sample mean being less than 15.5 is comes out to approximately 18.8%, so much lower. Now, does that mean that both of those pizzas will have less probability of being less than 15.5? No. You could have one that's 18 inches and one that's 13 inches. It just means that the average of those two is going to be closer to 16. So the probability of it being less than 15.5 goes down. What about with a sample size of 4? Well, now, once again, we're going to focus on that the sample size is normally distributed. The mean stays the same as in our population, but our standard deviation that we use in our formula changes. Okay, and it turns out the square root of 4 is 2. So just to be really clear there, right? That's what was going on there. The square root of 4 is 2. So that's why this one came out to be exactly 0.4. There's no rounding error introduced by just typing in 0.4 in the p-norm function. So the probability that the mean of 4 is less than 15.5 inches is now going down to 10.6%. So you can see that when we just randomly picked one pizza, there was a greater than 25% chance that it was going to be a small pizza. But if we did a sample of 4, now there's only a 10% chance that the mean of those 4 will be low.
I have a question.
Sure.
Do you recommend doing the chapter 4 assignment before Thursday's exam? Like, do they go hand in hand like that or no?
Well, it would probably help. But to be honest, if you get over the hump of the very first way to set up the very first question, I think the rest of it you could do very quickly. So I wouldn't waste time getting stuck in R stuff if you're struggling, and focus on the concepts for the exam. But if you feel like you're able to plug these p-norm, p binomial and the Poisson ones and actually work with them quickly in R, then it would definitely just strengthen you for the test. Okay?
All right, thank you.
Sure. All right, so what's going on here? Well, what's going on is as our sample mean, as our sample grows in size, the standard deviation every time was getting smaller. So if we graph the probability distribution for the sample mean, it's kind of narrowing in on that sample mean value. So it's narrowing in on this 16. Whoops, I meant to go that way. So it's coming in closer to that. Everything's pulling in. And the amount of area under the curve over here for what's underneath 15.5, the amount of area under this curve is going down as the sample size goes up. All right. So now comes probably one of the most powerful theorems in our modern world. And that is that for making statistical inferences, it is essential that the sampling distribution of X be normally distributed. So what if the underlying population is not normally distributed? So what if it's, there's a bunch of weird distributions out there. There's betas, gammas, binomials, we've seen Poisson. So what if the underlying distribution is not normally distributed? Well, the central limit theorem says something very powerful. It says for any population X with an expected value of mu and a standard deviation of sigma, again, not necessarily coming from a normal distribution, the sampling distribution of X bar will be approximately normal if the sample size n is sufficiently large. And if that sample size goes to infinity, it's exactly normally distributed. So the central limit theorem allows us to use all the information about the normal distribution and all the math and statistic that's been developed, and it allows us to use it on the sample mean. And that is huge, because without that, there's so many things we wouldn't be able to say with any degree of confidence. So it probably doesn't seem like a big deal to you, but if you've ever been sick and had to take a medicine, that medicine had to be approved by the FDA. And in order for that medicine to be approved, they had to do random samples. And those random samples had to then go through statistical analysis, which required that the sample means be obtained. And if it wasn't for the central limit theorem, nothing could be said about how the population in general may respond. Okay, so the type of distribution that X follows does not matter. The approximation steadily improves as the number of observations increases. And this is one of the reasons why you may have heard that whenever drugs are developed, they have to frequently run these ginormous studies. And the reason is because of this. The central limit theorem requires that in order to our approximation to really be normal, we need a really large n, and also to drive down that standard error that we looked at. So what's big enough? Well, big enough depends on what the question is. And in general, though, you are really close to a normal distribution if your sample size is greater than or equal to 30. So this is a rule of thumb. It's not written in stone anywhere, and it can change depending on how precise you want to be about certain things. But generally speaking, an n greater than or equal to 30 will get you there. Okay, so let's talk about an example. So for the month of May, a coffee chain advertised a happy hour between hours of 3 and 5 p.m. when customers could enjoy a half-price iced coffee. The manager of one of the chains wants to determine if the happy hour has had a lingering effect on the amount of money customers now spend on iced coffee. So before the marketing campaign, customers spent an average of $4.18 on iced coffee with a standard deviation of 0.84. So based on 50 customers sampled after the marketing campaign, the average amount spent is $4.26. If the coffee chain chose not to pursue the marketing campaign, how likely is it that customers will spend an average of $4.26 or more on iced coffee? So in order to answer that question, we are going to rely on the central limit theorem to help us understand the distribution on the sample mean. So the population mean, we're told, is $4.18 on iced coffee with a standard deviation of 84 cents. Since our sample is 50, and so that's greater than or equal to 30, we can then say that the sample mean is approximately normally distributed. And so because of that, we can say that it has a sample mean that's going to be the same as the population mean and a standard error of the sample mean, or the standard deviation, which is the original standard deviation, 0.84, but divided by that sample size. So we divide by the square root of 50. And that, I should have put squiggly equals, is approximately equal to 0.1188. So what is the probability that if you didn't run the campaign, what is the probability that your sample mean would have ended up being greater than or equal to $4.26, which was what you observed in your sample? So to do that, you would put this in this p-norm function, and you just put in the 4.26, which is the number you're asking about, right? The quantile, the value you're asking about, and we put in our mean and standard deviation that apply to the distribution of X bar. So that's why we put in these values here. They're coming from the size of our sample. So the mean is the same, but what's really important is that we're getting the 0.84 divided by the square root of 50. And And when we put that in R, we just pop out. And I'm going to just show you real quick how easy this is to do in R. Since I had it open, let me get it open again. Okay. So over here on my script, I could just say P norm, and it was 4.26, I think. And I think the mean was 4.18, if I remember right. And standard error is 0.84 divided by the square root of 50. So I put 0.84 divided by square root of 50. And just by doing that, I would get the area, we would get the probability that X is less than or equal to 4.26. But we were asking if it's greater than. So we want to say lower tail. And notice as soon as I started writing lower, I get my option. And I can just hit enter. And then I can just say false. Okay. So I hit control enter. And we see that we get our value over here in the console as 0.2503353. Okay, so it's just that easy. It's like a glorified calculator. So over here, I can just say example, central limit theorem, and I just can name this. If I wanted to, I certainly don't have to, but I could, and then I could just type that and I can see the value. All right, so just don't forget we can name objects. In any calculation, we can give it a name and use it later anywhere we want. Okay, so the sample mean observed that, and I think, oh, by the way, did I already tell you guys you get extra bonus points if you catch errors? So this should have, I did it right in the R, but I had it wrong in these notes. This should have said lower. Tail equals false. Oh, okay. All right, hold on, it's coming. There we go. So I had to put lower tail equals false. So because this is greater than or equal to, I'm required to put lower tail equals false, okay? All right, so now let's talk about the population proportion, which happens to be very useful in many applications. So we are concerned with this. So many applications, we are always concerned about this population proportion P. So recall that the binomial distribution will describe the number of successes X in N trials of a Bernoulli process where P is the probability of success. So if we want to know about an estimate of that proportion, the relevant statistic or the estimator is the sample proportion, which is just the number of successes divided by N. All right, so here's just a little bit of algebra. I'm going to see if I can do this. I'm going to tell you that this part right here is, and I don't know if it's going to let me shade this. I'd like to shade it out like in gray. So this is you're not responsible for this level of statistical derivation. I'm just showing you where it's coming from. But basically it's the expected value, and now we put what the definition of that sample proportion is. It's X over N. And then when you learn, if you were to take a more advanced statistics class, and I'm not sure if you did this in 210, you're able to pull out a constant. So this is equal to pulling out that 1n, and it's just the expected value of X. But X, remember, is coming from a binomial distribution. And so the expected value of X is N, the sample size, and the number of trials times the P, the population probability of success. And then the N's cancel, and you get back P. So because the expected value of our estimator is the sample proportion, this is an unbiased estimator. Okay, so that's the little bit of math that I believe the book skips. And you just have to believe them, but I just wanted you to see how easy it is to see that it's true. Okay, so when we look at the sample error on the standard error of the sample proportion, it's the square root of p times 1 minus p, or q, divided by n. By the central limit theorem, the sampling distribution, even though it came from this binomial distribution, it's also normal, with the mean of the expected value of the proportion, the sample proportion, and the standard deviation of being the standard error of the sample proportion. The rule of thumb, and this is based on a branch of statistics, and these rule of thumbs, by the way, come from this branch of statistics called asymptotics. And that's where they look out at taking things to limits, just like you did back in calculus. And so where does the distribution for this really start looking normal? Fairly close to normal. So the rule of thumb is it's when the number of trials times the underlying population probability of success is greater than or equal to 5, or when that and's important because you need both. The probability of a failure, 1 minus p times n, is also greater than or equal to 5. So let's do an example. A study found that 55% of British firms experienced a cyber attack in the past year. What are the expected value and the standard error of the sample proportion derived from a random sample of 100 firms? In a new random sample of 100 firms, what is the probability that the sample proportion will be greater than 0.57? Okay, so the way we would look at this is we'd say, okay, well, we know that some study, and this is where we're assuming this is a well done study, estimating the true population incidence of a cyber attack. Now, maybe they actually went out and talked to every single British firm. I doubt it, but anyway, so let's say, we have some confidence that this p equals 0.55 is legit. And then we're looking at a new sample. We take a random sample of 100 firms, and we find out that the proportion of them, the number of them that had a cyber attack, the expected value of that proportion, that sample proportion, is going to be the original p, the 0.55. And the standard error of that sample proportion is the 0.55 times the 1 minus 0.55 divided by the sample size, which is 100. And we calculate that out, and we get 0.0497. Now, we would check, what about NP? Well, NP is 55. That's certainly greater than or equal to 5. And N times 1 minus P is 45. And that's certainly greater than or equal to 5. So the central limit theorem approximation is valid. And because it's valid, everything goes back to this P-norm function again. Super easy. We just put in P greater than or equal to 0.57. We put in 0.57. We put in the 0.55, which we knew was our expected value of our sample proportion. And the only part that we have to be careful about is this 0.0497. And I went ahead and rounded. I maybe could have put in this whole thing. So the way I would have done this in R let's see if the numbers come out better. This is the last thing I'm going to cover. I'm going to just do this real quick. But if I were to go over to R, and we have the standard error of the sample proportion, P bar, and we're going to say that's the square root of 0.55 times 1 minus 0.55 divided by 100. All right, so run that. And so we can get an actual value. You see it's 0.04974937 is as far as R is showing it to us, and R actually goes out further in its internal memory. But so if we go back, we are going to use this pnorm function. Oh man, again, I needed to put lower tail equals false. So that needs to say lower tail equals false. Why am I doing that? Okay. Anyway, so let's go in and calculate this number. So it's 0.57. We want to know if the probability is greater than 0.57, 0.55, and then now instead of 0.0497, I'm going to use my calculated value here. Okay, so going over to RStudio, I can just say pnorm 0.57, and the mean was 0.55. And then for the standard error, I'm going to use this calculated value. And I'm going to say lower tail because I want the value above it equals false. So if I do that, I get 0.3438364. Okay. So going back to our data, 3438. So we were right there. The only issue is that this should have said lower tail equals false. Okay. So going back to R, we see that that's exactly what we got. We got this value over here. Okay. So I have a few more examples that we're not going to have time to go over, but I will have them in the slides and they will be on Brightspace. Okay, so maybe we'll start up with this a week from now.